So now that we've done step 8, we're basically, for example 1 at least, we're almost there for solving dHdt. However, we do want to look at step 9 because sometimes you plug everything in and you've still got more than one variable left. In other words, a variable more other than what you're trying to solve for. Remember, in this case, we're solving for dHdt, which is how fast the water level is rising in this rectangular prism of a tank. For step 9, you're going to determine the values for remaining variables. Okay, it's not necessary this time, only necessary if the equation still has 2 or more variables. This one already has 1, so we don't need to do step 9. I'm just going to go ahead and check this one off and move on to example 2. So for example 2, we had the ladder sliding down the wall. If you remember from step 8, we have 2x times 0.8 plus 2h dHdt equals 0. So in this case, you can see there's 3 variables here. So we need to find x and h before we can figure out dHdt, which is how fast the top of the ladder is sliding down the wall towards the ground. So we will be implementing step 9. We can determine x because we know the ladder's initial position, 1.5 meters from the wall, and the speed that it is sliding, 0.8. Let me give you some visual perspective on that. So if the ladder is initially 1.5 meters from the wall, and we know it's traveling 0.8 meters per second, then you can see that after 1 second, it's just going to be 0.8 meters more than that. So right off the bat, 1.5 plus 0.8 is 2.3, which will be x, which is the distance that's away from the wall. However, let's go ahead and mathematically show that. X equals 1.5 plus 0.8t. So if you wanted to know at time t equals 2, you could plug in 2 here. It'd be 1.5 plus 1.6. But just for 1, it'd be 1.5 plus 0.8, which is 2.3. And now that we know x, we can find h using the Pythagorean theorem. Remember, the goal is to get the equation in terms of, well, actually, it's in terms of one variable. We eliminate it down to one variable, so let me change it to 1. Okay, so here's kind of what we have right here. Here's the top of the ladder. Here's the ladder itself. Since we know it's 2.3 meters away from the wall now, after 1 second, if this is 5 and this is 2.3, we can solve for h by using Pythagorean theorem. We get h equals the square root of 19.71. And I'm just going to plug that into the formula. Actually, we'll do step 2. Step 10 in the next video. Sorry. But anyways, we figured out h and we have figured out x. So we have accomplished step 9 because we've determined the values for the remaining variables. For step 10, we're just going to plug those in, and then you'll see that you'll just have one variable left, the variable you're trying to solve for, in this case, the dHdt. Okay, let's look at example 3. We have the water filling into a conical tank here. And for step 7, we had this. For step 8, we were able to plug in 5 for R, and sorry, for H. So 5 represents the height of the water at that particular given time. We were able to plug in dVdt, which is 6. So if you notice and you look at this equation, you only have one variable left, dHdt, which is the rate at which the water is rising in the cone. So again, for this example 3, step 9, it won't be necessary because we already have the one variable we're trying to solve for. All we have to do is just isolate that variable. Moving on to example 4 with the coffee pot and the coffee filter. We are trying to figure out the rate at which the coffee is rising in the pot. Now, this one is going to be more involved, so it's going to take a little bit longer, but we talked about for step 8, we don't know the rate in which the coffee is increasing in the pot. But let's go ahead and read this together. So we're still doing step 9, but we want to figure out the values of the remaining variables. So we have to figure out this, the rate in which the volume is increasing in the pot, before we can figure out the rate in which the height is increasing. How can we figure this out? Go back to the picture and observe that the rate in which the coffee is dripping out of the filter will be equal to the rate in which it is dripping into the pot. So another reason why we want to draw a picture. So here's the coffee dripping down into the pot. If we can figure out the rate at which it's dripping out of this pot, so that's negative, right? Negative volume, that's losing volume in the filter, it's going to be increasing the same rate in the pot, okay? Assuming, of course, it's not evaporating away, right? So anyways, it's the same, right? It's the same coming out as it is going into the pot. So ultimately what we have to do is figure out the rate in which this coffee is dripping out of this pot. Now fortunately, we do know that it's falling at a rate of 1 inch per minute, and we know that the coffee on the filter is 5 inches deep as well. We also know the radius of this coffee filter, and we also know the height of the total filter. So we should be able to figure that information out, the rate at which it's dripping out of the coffee filter. So for step 9, we're going to use that information to figure out dV2 dt. So if we figure out dV1 dt, which is the rate at which it's dropping out of the coffee filter, it should be the same as it going into the coffee pot. Here we go. So if we can figure that out, we can figure out what we need to know. So we basically need to go back and look at the volume of our filter. Well, we know that the level in the filter at this point in time is 5 inches. We can see what? We can see another example of similar shapes. Here is the whole entire filter. It's 6 inches tall by 3 inches radius. So it's basically, if it's just 1 inch below that at this point, at 5 inches. There's 5 inches of coffee in this 6 inch filter. So we can figure this radius out. Since 3 is half of 6, then the radius now of the coffee in the filter is going to be 2.5. So we can plug in 2.5 in for R1. We know H1, and that will give us the volume of coffee in the filter. Okay? So this is just using similar shapes as we talked about before. R1 is just going to be half of H1, and H1 is just 5, so R1 is going to be 2.5. Another thing we can do, and I actually made this a little bit more complicated, we could just substitute R with 1/2 H1, so now we have 1/2 squared is 1/4, which is 1/4 H squared, and then 1/4 times H squared times H is H cubed, or H1 cubed, the height of the original coffee filter. So this is the volume, okay? Now we have the volume of the coffee filter now in terms of just the height. So it's 1/12 pi times H1 cubed. So if we know the height of coffee in this filter, we can figure out the volume now with just one variable using similar shapes. As we said, the radius of this coffee is just half of the height no matter what. Okay, so what from there? Well, since we have it in terms of one variable, we can now take the derivative. Remember, we're trying to figure out dV1 dt in order to figure out dV2 dt. The rate in which the coffee is dripping from the filter is the same as the rate in which it's going into the pot. So we're going to do some implicit differentiation using the power rule here. Move the 3 out, change this to a 2, multiply by dH dt. So we get the rate in which the volume is dripping from the pot is equal to 3 pi over 12 H1 squared dH dt. Now, as mentioned before, we know the height of the coffee is 5 inches in the filter, so we can replace H1 with 5. And the problem gave us the fact that it was dripping from the pot at a rate of 1 inch per minute. And we wrote that out for step 3, dH dt is equal to -1 since it's falling or dripping out of the pot. So we can plug both those things in to our formula and figure out that dV1 dt, the rate at which the coffee is the volume of coffee is coming out of the filter, is negative 25 pi over 4. Let's go ahead and write the units there. That'd be cubic inches per minute. Okay. So, I don't know if you noticed this. I've actually had this on here the entire time. Of course, that doesn't mean anything until we explain it, but that's the rate in which the volume of coffee is coming out of this filter. Negative 25 pi over 4 cubic inches per minute. As a rough estimate, that's about 20 cubic inches per minute. Okay, is coming out of this pot. So that means it must be going into this pot at the same rate. Positive 25 pi over 4 is how much the volume is increasing in the cylindrical pot. So all of that to say, we figured out dV1 dt to figure out that dV2 dt is just the opposite of that. It's positive 25 pi over 4. So we are still on step 9, but we've just figured out that dV dt2 over dt is equal to 25 pi over 4, and we have determined the value of that remaining variable. You can see that step 10 is going to be really easy. We're just going to plug that value in. So that's it for step 9. For this last example, as you could see, it was the most involved. But again, that's why it's called related rates. Conceptually, it makes sense that the rate in which this coffee is dripping out, the volume of coffee dripping out, must be the same going into this coffee pot. So that is it for step 9, determining remaining values. We're almost done with these problems. If you have any other questions about this step, let me know.